how to write it up on the board, but yeah.
This?
Yes, I guess we should probably scroll down to yeah.
Where do you want it? Here?
Yeah, that'll be it.
Yeah. Why don't you go ahead? And because Okay, we're going to get started. We've got a quick presentation on the study first, and then we'll get on with the lecture class.
Hello, everyone. My name is Colin Ferguson, and I'm a peer tutor at the study. The study is part of Transformative Learning, which is an academic resource center here on campus. We have two locations, the Study North, which is in Jewel Hall, right across from the Student Center, and then the Study Central, which is right over there in the Hillary J. Boone Center. All our tutors have an A or B in the class and are certified, so we are a great resource for this course. We provide study strategies and guidance for success in this course and beyond. Most people think you only need to come to the study if you're struggling in the course. However, that is not the case. It's also perfect for working on homework, connecting with classmates, and building skills in the same course. You can check our website for more information on tutoring schedule and locations for this course. The QR code is not up on the screen, but this is the website, and you can see what's right there. Don't wait until your final exam to come to visit us. If you come regularly to stay on track for your course. Do you all have any questions? All right, thank you all for your time.
Thank you. Thanks. Okay, I'm going to get started. Last class we talked about electrical attraction, repulsion. We talked about electric positive, negative charges as sources of electrical, origins of electrical attraction and repulsion. At this class we're going to quantify the electrical attraction and repulsion, the electrical forces between electrical charges. So specifically in this class, I want to go through the 3 bullets on the screen. So the first one is to introduce Coulomb's law. It's the law for the electrical force, how the electrical force works. It's the law that describes the electrical force between a pair of charges, between 2 charges. So we're going to do that. Second bullet is what's called the superposition principle. The superposition principle applies to electricity. It applies to gravity also. And it's a principle that describes or allows you to deal with collections of charges rather than just the interaction between a pair of charges. So we'll talk about the superposition principle. And then third bullet, throughout the class, we're going to look at some illustrations, some examples, some problems involving Coulomb's law, involving superposition principle, to get some practice with Coulomb's law and superposition. So that's the plan. And I'm going to begin with that first topic, introducing Coulomb's law. I got a few slides on Coulomb's law. The first one, I got a slide just how did Coulomb come up with Coulomb's law. So we'll talk a little bit about that. And then I've got 2 or 3 slides actually describing Coulomb's law in words, describing Coulomb's law as an equation, describing Coulomb's law in pictures to get us familiar with Coulomb's law. Coulomb's law is really the kind of like the capstone on what we discussed last class, where we discussed the discovery of electrical attraction. We discovered that all objects are electrical in nature. We discovered that there's actually electrical attraction and repulsion. On top of that, built on top of that, was Coulomb's law, is Coulomb's law, that describes precisely, accurately, that electrical attraction and electrical repulsion between charges, how charges work. Okay, so Coulomb, Charles Coulomb, Coulomb was a French engineer. And Coulomb was a French engineer that built canals and built bridges. And he used his engineering skills for his hobby, which was understanding electricity and magnetism and working on electricity and magnetism. And he built a device, an instrument, to accurately, precisely measure the tiny forces that he created between electrical charges. And through doing this experiment with this device called a torsion balance, he was able to map out the sizes of the electrical forces between electrical charges and write down a law, Coulomb's law, that describes the electrical forces between electrical charges. This sketch here, this is the torsion balance, and I'm going to show you a video of the torsion balance so you get a better idea of the torsion balance. But basically a torsion balance is a long vertical wire or long vertical fiber, here it is. Attached to the bottom of the wire is a horizontal beam that is balanced with objects on either side of the beam. The fiber is supported at the top. That fiber, if you were to twist that fiber, if you were to physically twist it, or or an electrical force was to twist it, that fiber, like a spring, if you pull it or stretch or squeeze a spring, it pushes or pulls back when you try and stretch it or squeeze it. If you try and twist this fiber clockwise or counterclockwise, it's gonna twist back. And he used that property to develop the torsion balance to measure the forces that are created by electrical charges. So over here is a fixed sphere in blue, a free sphere on this fiber in red. He applied charges to the spheres, and those charges would repel one another if they're like charges, and that causes the wire, the cable, the fiber to twist, and the amount of twist, how many degrees of twist, reflects the size of the force, allows him to measure the force, and this is how he mapped out the force between electrical charges. So that's how it all works. I'll show you a video of it in action. I mean, it's a cartoon video of it in action. Here we are. This is the torsion balance again. Here's the fiber. You can see that pretty clearly. Downstairs here are on the left is the fixed sphere. It's a conducting sphere on what we're going to put some charge. And touching it is the free sphere, the one on the fiber. That's on the right. And we're going to put charges on these. And you're going to see as I run the video, a plunger come down that has some charge, that was charged up, on which charge was harvested, and it's going to charge up these two bottom spheres. The charge is going to, because those spheres are touching, the charge is going to spread out on those two spheres. They're going to become equally charged with the same size of charge, so they're going to repel one another, and we'll see the torsion balance in action. Fantastic video. So we're getting a close-up here. This, again, was the fixed sphere. This is the free sphere that's on the horizontal beam, that's on the vertical wire. And we're getting a good view of that arrangement here. And look, here comes another object that is charged up. It's going to touch these two spheres. It's going to spread charge out onto those two spheres. They're going to repel. This one can't move. This one does move. The wire twists, and the number of degrees by which the wire has twisted told Coulomb the electrical force between these two charges. And it was using this device, which was a big discovery, big instrument discovery, that is used in many other situations for measuring small, tiny forces. It's with this device that he mapped out his law. He mapped out Coulomb's law for the electrical force between pairs of electrical charges. Okay. So now I've got a couple of slides in which I'm going to describe Coulomb's law. I'm going to describe it in words, and I'm going to describe it as an equation and a diagram. We're going to do all those things because somehow in our minds we've got to get some sort of symbolic representation of Coulomb's law and how electrical forces work. That's what we're going to try and develop, that we understand in our mind in some way how Coulomb's law electrical forces work, because we've got to apply it, we've got to use it in problem solving. It's kind of like, you know, elephants and mice, right? We all have some idea about elephants and mice. If I think about elephants, I think about a trunk and them being big. If I think about mice, I think about them squeaking and being small. We've got so that's a representation of what a mouse is and an elephant is. It may or may not be very accurate. We've got to somehow get an accurate representation of the electrical force, the Coulomb force between electrical charges, because we've got to solve problems involving electrical forces between electrical charges. So I'm going to describe this force in words. You might like that. I'm going to describe it in equations. You might like that. I'm going to draw a picture of it. You might like that. We're building up this representation. Okay, so properties of the electrical force. Last class we actually discovered that the force must get weaker with distance. It must shrink as the distance between charges grows. What Coulomb found is it gets weaker in a very special way. It gets weaker with the square of the distance. That is, if you double the distance between a pair of charges, twice as far apart, then you get 1/4 of the strength of the electrical force. So it's 1/2 squared. If you triple the distance between two charges, then you're going to get 3 squared is 9. You're going to get 1/9 of the force between the two charges. So that's the distance dependence of the electrical force between a pair of charges. It's what we call a 1/r squared, an inverse square law force. And so that was a big discovery. I've written that down here. The force between a pair of charges is proportional to the product of the two charges. So if you make one charge bigger, that's going to create a bigger force. You make the other charge bigger, that's going to create a bigger force. You make both charges bigger, that's going to make a much bigger force. It depends on, I called it Q1 and Q2 of the two charges. It depends on Q1 times Q2. So it depends on the product of the charges. And this is a force that charge 1 would experience due to charge 2, and charge 2 would experience due to charge 1. So they're the same size forces that are experienced by the two charges, and they're just in proportion to the product of the two charges. Another important point, third bullet. That force between the charges is always directed along an imaginary line, not a real line, but an imaginary line drawn between the two charges. So imagine a line between two charges. The force acts along that. It acts towards the other charge if it's an attractive force, if they're unlike charges. It acts away from the other charge if it's a repulsive force, i.e. if they're like charges, two positives or two negatives. So that's another ingredient in Coulomb's law. And finally, I just mentioned this one here. It encodes with plus and minus signs mathematically the fact that like charges repel one another, whereas unlike charges attract one another. This key feature of electricity that's quite different from gravity. Okay, so that's the force in words, if you like words. And it looks like we're not going to get any further than that. Oh, here we are. This is the force in pictures and in equations or formulas. And as I say, by doing it in words, pictures, and equations, we're building a representation of how the force works. In the pictures here, I'm just sketching some of the properties, not all of the properties, as the force between a pair of charges. Over here on the left, this is a pair of like charges, two positive charges as an example. Over there on the right is unlike charges, a plus and a minus charge. So we're picturing the cases of repulsion and we're picturing the cases of attraction on the left and on the right. On the left, I've also, and on the right, drawn this imaginary line, this dashed line here, along which we said the forces act. The electric force acts. It always acts along that line. In this particular case, that force acts along that line, but away from the other charge, because this is the repulsive case. So here's the force on charge number 1 due to charge number 2. It's directly away from charge number 2. Here's the force on charge number 2 due to charge number 1. It's directly away from charge number 1. Here's the other case. This is the case of electrical traction. Again, the forces are acting along the line drawn through the two charges, but this time force charge number 1 is being attracted to charge number 2 because it's the opposite sign, and charge number 2 is being attracted to charge number 1. So all that working of Coulomb's law, electric force law, is included in the picture. It also shows you that no matter what the values of Q1 and Q2 are, the two forces are always equal and opposite one another. No matter whether one charge is small, one charge is big, the forces, the sizes of the forces are the same, the directions of the forces are opposite one another. All that's built in the picture. Here's an equation. Here's an equation for, this is Coulomb's law. This equation describes the strength, the size, the magnitude of the force. That's why I put the vertical bars here. That means magnitude. That means size. How big the force is. It means I'm not writing down this equation describing the direction right now. I'm just describing the size. The size goes as the inverse square of the distance. So we see the square of the distance in the denominator. It goes as the product of the two charges. We see the magnitudes of the two charges in the numerator. And this k here, this k is a constant. It's a constant, has a certain value, 9 times 10 to the 9 newtons meters squared per coulomb squared. It's a constant in every equation you'll do with the electric force, with the Coulomb law. And it's a constant that characterizes the strength of electricity. It represents the strength of electrical forces. So that's the constant K here. Okay, so that's Coulomb's law in pictures and words. I just wanted to make a few more remarks about this. We've gone the wrong way. We're going to spend half the class with me trying to do that. Here's a few final comments. The value of the Coulomb constant, as I mentioned, which characterizes the strength of electricity, is about 9 times 10 to the 9 Newton meter squared per Coulomb squared. The units are just so that the units of the equation are the same on the left-hand side and the right-hand side. There's a similar constant in gravity, which is the gravitational constant, or Newton's constant. That, by comparison, is 6.7 times 10 to the minus 11 Newton meter squared per kilogram squared. So the electric one, is actually a very large number, and the other, the gravitational one, is actually a very small number. And this is related to the fact that, and we'll see this in more detail, the gravitational force is a very weak, feeble force compared to the electrical force. That's a much stronger force. What else was I going to say? Oh yeah, just a remark of, we introduced these units of coulombs for measuring charge. when you do demonstrations or when you do experiments where you rub the glass rod with some silk or cat's fur, or you rub the plastic rod with silk or cat's fur, and you charge up the glass rod and the plastic rod, the amounts of charges involved in that rubbing are normally nanocoulombs or microcoulombs, tiny fractions, 10 to the minus 9, 10 to the minus 6 of a coulomb. So those were the amounts of coulombs that we were dealing with in the last class. I also said that nature comes in little packets of charge, and those little packets of charge, those are even smaller, right? They're minus and plus 1.6 times 10 to the minus 19 coulombs for an electron and a proton. So a coulomb is actually a very large amount of charge. We don't normally see a coulomb of charge exposed. In experiments, it's more microcoulombs, and the electronic charges are order 10 to the minus 19 coulombs. The other comment I wanted to make, the last one here, is that we should remember, it's important to remember, that this law, no matter what an achievement it is, and it is a real achievement, it only applies to a very special case, the force between 2-point charges. And in most situations, we actually don't meet just 2-point charges. We're going to have to deal with this. Now, in reality, it actually applies to the force between 2-point charges, or things that are effectively 2-point charges, which means the size of the charges is much smaller than the distance between the charges. So there's really no such thing as a point charge, but there is such thing as a charge whose size is effectively a point compared to the distance between the neighboring charge. Okay. So I want to look at a couple of examples of applying Coulomb's law now. So we've got this mental representation now through our words and our pictures and our equations of how Coulomb's law works. Let's get going and solve some problems. Okay, this is the first question, the first problem. We're asked to compare the strength of the electrical force and the gravitational force, one we met in this class, one you met last semester, in a hydrogen atom. So a hydrogen atom is a combination, as you know, of a proton and an electron separated by some distance. The proton and electron have charges so that they experience an electrical interaction. The proton and the electron also have masses, so they experience a gravitational interaction. So we're going to compare the relative strength of the gravitational and electrical interactions between the proton and the electron. And this is one way we could compare, how much stronger is electricity than gravity? We can get a quantitative idea of that. Now, you might say, well, why didn't you compare the electrical forces between two 1 coulomb charges with the gravitational force between two 1 kilogram masses? Why didn't we do that? We didn't do that because we just made up those units, kilograms and coulombs. What we're doing is comparing the forces of gravity and electricity between something fundamental in nature, the most basic atom in nature. What is the comparison of the forces of electricity and magnetism between the components of the most basic atom in nature? So that's why we're doing this. Okay, so on this slide, I've made a picture of the problem. Here's the electron on the left, here's the proton on the right. I indicated the separation of them. I called it R in the hydrogen atom. I listed some numbers that we're going to need. We need some properties of the electron, its charge and its mass. These are tiny numbers, but I wrote them down here. We need some properties of the proton, its charge and its mass. I wrote them down here, tiny numbers again. But the charges are equal and opposite. The masses are very different. The proton's heavy compared to an electron. The electron's very light compared to the proton, like a mouse and an elephant, basically. And there are two more numbers I wrote down here. We mentioned these earlier on. The gravitational constant characterizing the gravitational force, and the electric constant, Coulomb constant, characterizing the strength of the electrical force. I wrote those numbers down. All these numbers we're going to have to use. Okay. So I'm going to go over to the document camera. And risk attempting to demonstrate my handwriting. I've written down on here, not very clearly, the charges that are involved in this problem, the masses that are involved in this problem. I actually forgot to write down the gravitational constant and the Coulomb constant on this sheet of paper, but we can look it up in the notes. Okay, so my job is to calculate the ratio of the electric force, this is Fe, to the, and it's not very clear, is it? To the, that's better, to the gravitational force. The vertical bars again are just that I'm only going to worry about the sizes of electric gravitational forces. I'm not going to worry about directions, whether they're attractive or repulsive or whatever. They're both attractive, but I'm not worrying about that. I'm just worrying about the sizes. Okay, so how are we going to do this? This is the comparison of electric force with gravitational force. Well, I'm going to fill in Coulomb's law. For the electric force, that's in the numerator. Coulomb constant times the product of the charges divided by the square of the distance. It's an inverse square law. I'm going to fill in Newton's law. Oh, you idiot. For the gravitational force between the masses, it's the gravitational constant times the product of the masses divided by the square of the distances between them. Couple of things about this. Here, the 1 and the 2, the subscripts Q1 and Q2 and M1, M2, that's really going to be the electron and the proton. So I could have wrote QE and QP. That would have been better, but I've written Q1 and Q2 now. I could have written ME and MP. That would have been better, but I've actually gone ahead and written M1 and M2. So that's one point. Another important point is actually both these laws are inverse square laws. So there's a division by r squared in the numerator, division by r squared in the denominator. Those r squareds cancel each other out. So that's why I didn't need to know the distance between the electron and the proton to be able to compare the electric and gravitational forces between the electron and proton. All I've got to do is calculate this ratio here of Q times the charge of the proton times the charge of the electron divided by G times the mass of the electron, the mass of the proton. And all those numbers, 4 of them I've written down on this piece of paper, 6 of them I wrote down on the slide. I can just plug them all in. Now, it will take me literally 20 minutes to write all that out, and I will make mistakes. So I've already calculated the answer. If you plug all those numbers in, the answer comes out to be about 2 times 10 to the 39. That's an enormously large number. It's an enormously large number because think about the constants, K and G. K is order 10 to the 9. Coulomb constant was 10 to the minus 11 or whatever. Newton's constant was 10 to the minus 11 or whatever it is. So that's a really big number over a really small number. That's going to make a huge number. Also, the charges over the masses. The charges are small numbers. The masses are also small numbers, but the small numbers for the charges are actually much bigger than the small numbers for the masses. So the ratio of the charges over the ratio of the masses is also a huge number. So this is why this number comes out to be so large. I know of no bigger number that you're going to meet in physics 211 or physics 213 than this number here, which is the ratio, the strengths of the electric and gravitational forces in an atom, in a hydrogen atom. Almost 10 to the 40. Almost 1 with 40 zeros over it. So electricity is not just bigger than gravity, it's massively bigger than gravity. It's hard to imagine. Why do we ever see gravity? The reason we do see gravity, for example, the gravitational pull, experience gravity, the gravitational pull of the Earth. So gravitational pull of the Earth on you or I is a sum of gravitational pulls between the atoms of you and the atom of the Earth. The electrical pull between the Earth and you or I is the sum of all the electrical forces between all the atoms of you and all the atoms of the Earth. Now those individual electrical forces are way bigger, 10 to the 40 times bigger than the gravitational forces between the atoms of the Earth and the atoms of you and I. But, this is the key point, but the gravitational forces are always, always attractive. Every atom of me is being attracted to every atom of the Earth. Whereas the electrical forces, due to the electrical components of the atoms, they're both attractive and repulsive. So the electrons in me are being attracted to the protons in the Earth. But the protons in me are being repelled by the protons in the Earth. And that perfectly cancels out. So the only reason we see gravity is because it's not that it's somehow strong, it's actually incredibly weak. It's just because the electrical force for neutral objects cancels out. Okay. Second example. Okay, I'm going to show you a little movie of this just to give you an idea. Because I had a really good idea last night. I was a little bit jealous of Coulomb discovering the force between electrical charges, or quantifying the force between electrical charges. And his torsion balance. And I was thinking about it. I came up with a new way of measuring tiny forces between electrical charges. And I want to show you the video of this. I've gone blank, and I can't remember how to change the... Here we are. So this is my idea. I thought Coulomb's torsion balance was pretty clever, but this is my idea. I'm going to suspend two very light conductors called pith balls from these two long strings. Here they are suspended, and of course they're suspended there, they're hanging under the influence of gravity, so they're hanging vertically down. I'm going to bring up some charge to the two conductors, and I'm going to deposit it on those two conductors. Since they're touching, it's going to spread out amongst those two conductors, and they're going to repel from one another, and they will no longer hang vertically. And because they no longer hang vertically, the angle that they hang at to the vertical will tell me how much charge I put on those conductors. I've got a new device for measuring charge or exploring Coulomb's law. So this was exciting for me. And so let's watch how it works. Again, I've gone back to the plastic pipe and the cat's fur, and I'm charging up the plastic pipe by rubbing. We know how that works. I touch the two balls, and now, look, they're no longer hanging vertically. They're hanging at some angle to the vertical, and that's because they're no longer under influence of just gravity and the tension in the string. They're repelling from one another through the electrical force, and the angle at which they hang will allow me to figure out the charges on those two balls. So let's see if we can use that idea here. Use that idea to solve this problem. So we're told that the two spheres that I applied charge to had mass 5 grams. they were on strings that had length 40 centimeters, 0.4 meters. When I touched them, because they were already touching themselves, the charge spreads equally onto the two of them, so they're equally charged with the same sign of charge. And when I do that, they hung at 20 degrees. From that information, I can calculate the force, electric force between the charges, and I can calculate the charge that I had deposited on the charges. This is an electroscope that I just invented overnight, an electroscope for measuring charge. Okay, so let's get going with this. I'm going to do this also on the document camera. I've already started it. I started it by drawing a picture of the problem. On the sketch, I got the left-hand string and sphere here. I got the right-hand string and sphere over here. I've called the length of the strings, it was 40 centimeters. I called that uppercase L. Called the masses, those were 50, was it 50 milligrams, 5 milligrams? That's the M here. These angles, that's the angles to the vertical, that was 20 degrees. And here I marked, I called it R, it's the separation between the two masses, between the two charges. And I actually, just with a little bit of geometry, I calculated that based on the length of the strings and the angle at which they're hanging. You see, these two strings form right-angled triangles. The opposite side, opposite the angle, we can calculate by sine theta. L sine theta, the length of the string is the hypotenuse, and so 2L sine theta is the little bit of geometry, it's the distance between the charges. And so I did 2 times L, that's 40 centimeters, times sine of 20 degrees. That gives me the separation between the charges, and it came out to be about 27 centimeters or 0.27 meters. So I already did that bit of geometry. I did it ahead of time because it's not really the physics bit, it's the geometry bit. Okay. So how am I going to solve this problem of what is the charges on the two spheres? The way I'm going to do it is first solve the problem as what is the electrical force between the two spheres. And then once I've got the electrical force between the two spheres, I'm going to solve for the charge on the two spheres. We're going to do it that way. Therefore, how am I going to find the electrical force on the two spheres? What principle am I going to use to find the electrical force on the two spheres? The principle I'm going to use is that the sum of the forces on either the left-hand sphere or the right-hand sphere. So either this one or this one. I could think about either. Maybe I'll think about the right-hand one. The sum of the forces, this is sum, this is the force vector. The sum of those force vectors is 0. If those spheres are just hanging there with some separation at some angle and just stuck there in space. So I'm going to use the fact that the sum of the forces is 0. I'm going to write down the forces, sketch the forces in a moment, but the forces are gravity on each sphere, that's Fg. They're also electricity, Fe, because they're charged spheres as well as massive spheres. And there's also tension in the string. So there's a tension in the strings. So there's a tension force. I call that T. And these must add up to 0. So that's the key ingredient. Let me draw a few of them. Here's Fg. That's the force of gravity acting on this right-hand sphere. Here's Fe. That's the repulsive force of electricity that's acting on the right-hand sphere. And here's tension. That's the tension force in the string that acts along the string. And it must be that those three force arrows, Fg, Fe, and T, they must add up add up as vectors to give 0 net force, because that sphere is just sitting there in space and not accelerating. Okay, so that's my basic principle. That's the key idea for solving this problem. Now, I'm going to rewrite this sum of the forces now. I'm going to rewrite it, rather than in terms of vectors, I'm going to write it in terms of the horizontal and vertical components of the vectors, the horizontal and vertical parts of the vectors. This is a technique you've done in 213, 211 a lot. You break down forces into their component parts, horizontal and vertical, for example. And so we're going to do that. So let me write that down, and then I'll say a few words about it. I can't speak and write at the same time, so I'm going to write it all down and then talk about it. The top equation, that's when I think about the vertical components of the forces. So let me put a little v here. And the bottom equation, that's when I think about the horizontal forces. Let me put a little h here. So vertically, what forces are acting vertically? Well, there's gravity that only acts vertically, that's straight down. So here's gravity, and the plus sign here means I picked downwards to be the positive direction. But there's also another force that's acting vertically. It's a component of the tension force. See, the tension force acts up and towards the left. It has a vertical component and a horizontal component. And so it's the horizontal component, vertical component, that is the T cosine theta. Is this side of this right angle triangle. This angle is theta, like this angle is theta. This is T cosine theta. It's in the opposite direction, so I put the minus sign. So that's the forces in the vertical directions. No electric force in the vertical direction. What about horizontal direction? In the horizontal direction, there's the other component of tension. There's a horizontal component of tension. It's T sine theta. I called ridiculously left to be the positive direction, but that's my convention here. So plus T sine theta. There's a tension force to the left, but then the electrical force is acting towards the right in the opposite direction. The entire electrical force acts towards the right, and so that's minus Fe that I've written here. And these two must add up to 0. So this is a rewriting of the fact that the forces on the sphere add up to 0. We did it for the right-hand sphere, could have done it for the left-hand sphere. You get the same equations either way. Everybody okay with that? Good. Time for a stretch, and let's get on with solving this. In that equation, there's some things we know. We knew the directions of the forces. We also know pretty easily the gravitational force. It's mg, and we know the mass. So if we know the mass, and we multiply mass by 9.8 meters per second squared, the gravitational force is 0.0949 newtons. So we actually know the gravitational force. But we don't know the size of the tension force in the equations, and we don't know the size of the electrical force in the equations. And so now I'm going to go about the business of finding out what tension and the electrical forces are, based on my knowledge of the gravitational force. I'm only finding out what tension is because I need to find it out to find the electrical force. We're only interested in electrical force. So I'm going to use equation, the first equation, the one for the vertical. I'm going to solve it for tension. Let me shoot this up a bit here. Give myself some room. Tension in the string using the vertical equation is Fg, we know that, remember, divided by cosine theta, cosine of 20 degrees. Simple as that. All I got to do is divide 0.049 newtons by 20 degrees. I did that, and I got 0.052 newtons. 20 degrees is close, the cosine of 20 degrees is nearly 1. I don't know what it is, can't remember what it was, but it's nearly 1 because the angle's small, pretty small, and so that makes the tension force a little bit bigger than the gravitational force. So now we've got tension. Now I can use the second equation to find out what Fe is. To take the second equation, move Fe over to the right-hand side from the left-hand side, it says that Fe equals the tension times the sine at 20 degrees. Well, I know now that the tension is 0.052 newtons, just going to multiply it by sine of 20 degrees. Sine of 20 degrees, on the other hand, is a pretty small number. So it's going to make this force smaller than tension and gravity. And I already computed what that is. It came out to be 0.018 newtons. And so that's the electrical force. Let's sit back and bathe in the fact that we've just solved for the electrical force in this particular problem. We've used our understanding of forces to solve for the electrical force. Now we're going to use Coulomb's law. We're going to use Coulomb's law, we're going to turn around Coulomb's law and solve for the charge that's created this electrical force. So finally get to Coulomb's law. Coulomb's law for the electrical force is it's the Coulomb constant times the product of the charges. Add charges, remember we said they're both Q and Q. So the product of them is Q squared. And Coulomb's law says to get the force we divide that by the separation between the charges, which is R squared, which is at 27 centimeters squared. So all I got to do actually is turn this around. Q will be equal to, if we rearrange this, R times the square root of Fe divided by the Coulomb constant. So basically, I moved the Coulomb constant over to the other side of the equation. I moved R squared over to the other side of the equation. I took the square root. Everything on the right-hand side now, R, Fe, and K, we know all those numbers. All I got to do is plug them in. Again, I'm not going to write it all out because it takes me too long. I'll make a mistake. I'm just going to imagine, let's imagine I wrote it all out, plugged in the numbers, and I came up with the charge, and the charge came out to be 0.38 micro, 10 to the minus 6 coulombs. And so, indeed, from my understanding of forces, my understanding of Coulomb's law, I was able to use this device to extract from measuring the angle of the two balls on the string, determine the charges that I'd applied to the string. It's an electroscope for measuring charges. Okay. Everybody okay with that? Kind of. I guess that's the vibe I've got. Yeah?
Where did the 0.49 newtons come from?
That came from right down here. I said that the gravitational force is, what's the one thing you might possibly remember from 211? Gravitational force equals mg. And g is 9.8 meters per second squared. So I just multiplied the mass that we were given of the spheres by g.
Okay.
And so I kind of knew gravitational force. So that's a good point to remind us of that. Yeah?
Where do you get 20 degrees?
Where did I get 20 degrees? That was in the problem. Here. So we were told the strings were hanging at 20 degrees. I measured the strings to be hanging at 20 degrees. If we didn't know the angle which the strings hang, we couldn't have solved the problem. So it all relies on that. Does that make sense?
Sort of, but the problem I'm looking at is 2 degrees.
The problem you're looking at is 2 degrees. The one I have in the slide, the one I have in the slide,
Okay, so it's a typo.
It must be a typo somewhere. Where is it? Is that from a previous class or something?
I downloaded it Tuesday.
Oh yeah. So maybe yeah. So here's a good point. I sometimes change my slides before the class. So if you're downloading your slides, because that's helpful, right, on your iPad to annotate during the class, you might want to download them close to just before the class, because you're confused because Tuesday I had a different numbers in the problem, and then I changed them for this class because I thought 2 degrees, well that's almost vertical, let's make it bigger and more obvious. So I made it 20 degrees. Yeah. These are good questions. I would encourage you to always ask questions. If you don't get something, probably 90% of everybody else gets something, and maybe I know it, or maybe I don't, and I'll have to admit it. So ask questions. Okay, let's move on. Superposition principle. This is how we handle arrangements that are more than a pair of charges, because we're very limited right now with Coulomb's law. Here's the basic idea. So I'm going to picture it here. This sketch shows 3 charges with these different colors. So there's a charge, I called it charge number, what did I call it? Where's charge number 1? Charge number 1 is here. It's in, I don't know what color this is. Is this teal or something like that? So this is charge number 1, and then nearby it are charges 2 and 3. In olive here is charge number 2, and in orange here is charge number 3. So this is a problem that is immediately beyond the scope of Coulomb's law, because Coulomb's law is about 2 charges. This has got 3 charges in it. So how do we deal with a problem involving, say, 3 charges or more charges? So supposing I'm interested in the question, what is the force on charge number 1 in teal due to charge number 2 in olive due to charge number 3 in orange? Superposition principle tells us how to deal with that. To find the total force on charge number 1 due to 2 other charges, you just add together the force vectors based on Coulomb's law due to the force of charge number 2 on charge number 1, olive on teal, and charge number 3 on charge number 1, that's orange on teal. So we just have to add the 2 forces. In olive here, I pictured the force due to charge number 2. Remember, it's going to be along the line between the 2 charges, and it must be opposite charge because it's attractive here, you see. And I also pictured the force between the orange charge and the teal charge. That's this orange arrow here. Again, it's along the line, but these must be like charges, so it's a repulsive force. So all we've got to do to find out the force on charge number 1 is add the Coulomb forces from charge number 2 with the Coulomb force from charge number 3, remembering that these forces are vectors and we have to add them as vectors. I pictured the vector result here. This is the net force due to the two individual forces on the individual charge due to charges 2 and 3. How did I get that vector? Well, let me just remind you of how we add vectors. How do we add vectors? I'm reminding you here visually, pictorially. In an example problem, I'll show you how to add vectors numerically, algebraically. But how do we add them visually? Well, the way to add 2 vectors together is draw the first vector. So I drew here the olive vector of the olive charge due to charge number 2. It was this one here. And then to add the second vector, you start at the tip of the first vector. You draw the second vector, that's the orange vector, due to charge number 3, the orange one. And your final vector runs from the tail of the first vector to the tip of the second vector. So this is a picture, a visualization of vector addition. So it's as simple as that, as adding together arrows, right? I got one force that kind of went like this, got another force like this. I add them together and I get from the tail of the first to the tip of the second, this resulting force. Everybody okay with that? So this is marvelous, because we would have been stuck with just being able to solve problems between a pair of charges. Now, in principle, we can solve problems between any arrangement of charges. We just got to superimpose all the little forces between all the little pairs of charges to get the total force on the charge we're interested in. So, good job. Time for a quiz question. Again, this one doesn't count for credit. Next week, we start counting for credit. When we start counting for credit, you'll get 2 points for a correct answer. You get 1 point for incorrect answer. And if but the answer has to come in with this, within the sort of, period that I'm setting the quiz. So you can't, like at the weekend, try and catch up on quiz questions because I'll see them as late. So it's in-class quizzes. Completely forgot what I'm doing. Where I'm going. Oh, I'm going here. What time is it? It is 10:25, and so I better change this to like 10:28. I'm not going to give you much time because I'm panicking, and they're not counting for credit. And again, feel free to talk with one another, discuss it, argue about it, no fighting. But you're going to have a couple of minutes to respond to this one. The question involves two charges placed on the horizontal axis. They're like charges, so they're both positive or they're both negative. And then we're going to put a third charge on the axis, and we're asked to figure out in what region, A, B, or C, is it possible, with these two like charges Q1 and Q2 present, is it possible, and where would it be possible, that we could add a charge where the net force on that charge due to Q1 and Q2 is actually 0? Okay, let me give you the answer. Let's check we're all on board with the answer. We've got two charges on a horizontal axis. Let's imagine the front of the desk is the horizontal axis. Let's imagine the two deflated balloons here are the two charges. They're the same sign charges, so they're either both positive, both negative. The different colors here just indicates one's on the left and one's on the right, but they are the same sign charges. Is it possible for me to place a third charge somewhere along this line that goes through those two charges where it actually experiences no net electrical force? It actually experiences a sum of the forces from the two other charges, the green and the red one, that add up to 0. The answer is, firstly, yes, it is possible. In this case, if they're like charges, the location that you have to put the third charge for the forces to cancel out from the blue and the green charges is somewhere in between. If you put it somewhere in between, I don't know where in between because I don't know the values of the charges, but it's going to be somewhere in between. One of the charges will exert a force towards the right, and the other one, because it's the same size, would exert a force towards the left. So the forces from the like charges, if you put a charge between them, are in opposite directions. So you could pick a place where they're not only in opposite directions, but they exactly cancel out. So the answer is to put it in between. If you put it over here, the third charge on the far left, then because they're like charges, they'd either be both pushing towards the left or both pushing towards the right, so they could never cancel out. If you put the third charge over here on the right of both charges, again, the forces on the third charge would either be both towards the right or both towards the left, so it could never cancel out. So you understand superposition, you understand it's in this region where you can have equal and opposite forces that cancel out, and that's a superposition. Everybody okay with that? Good. Example of superposition. So I'm going to give you a quantitative example of superposition principle. It's an interesting one. I mentioned salt water in the last class because we're bags of salt water and salt water is a conductor. I'm going to mention salt grains in this class because it's an example of the binding of atoms together in matter. And actually, just to complete the story, we'll talk about water in the next class because it's a very interesting molecule. And then we'll make our salt water and we'll be humans again. So, here's an interesting question. Here's a grain of salt, sodium chloride salt. And as you know, it's made out of sodium and chlorine ions. The sodium are positive ions because they like to give up their electron, and the chlorine are negative ions. They like to get an extra electron. And so in a salt crystal, we get this regular array of sodium and chlorine ions. But if you think about it, in that array, there's attractive forces between unlike charges, so between a chlorine and a sodium. And there's repulsive forces between like charges, between pairs of sodiums and pairs of chlorines. So why is it that matter is ever stable? Why is sodium chloride ever stable? Why is matter stable when you've got inside the matter these charged building blocks that have equal numbers of attractive and repulsive forces? So that's an interesting puzzle. And the fact that matter substances are stable is one of those emergent phenomena that came out of there being this basic dimension of charge that comes in two categories, positive and negative. Out of that, we've suddenly got this emergent phenomena of matter, atoms clumping together to form solid materials, solid substances. So, but why does that happen if there's attraction and repulsion? Well, we're going to see why that happens. Okay. Rather than see why it happens for some big old sodium chloride crystal, I'm going to imagine a little nano crystal of sodium chloride that's just made up of two sodium ions. They're positively charged. They're in magenta here. And two chlorine ions. They're negatively charged. They're in green here. And they're in a regular array, a regular lattice, and their separation, I've called that separation A. So here's my nanocrystal, or my microcrystal, and what I'm going to do is calculate the force. I could calculate it on any one of these ions. I'm going to calculate it on this top left ion. What is the net force on this top left ion? This is a problem that's going to need Coulomb's law. It's going to need superposition principle because we got combinations of pairs of charges. And what we're going to discover is, although there's attraction and repulsion going on, the attraction wins over the repulsion, and we bound together the ions to make matter, to make a solid material, solid substance. This is how it works. This is how this effect emerges. And this is why we're all stuck together, not falling apart. Okay, so let's go ahead and solve this problem. This slide, I sort of introduced the principle of finding the force on the top left charge, and I also make a sketch of the forces on the top left charge. So let's just go through this. I'm not going to do this one on the document camera. I'm not going to do this one on the document camera because it's too much for me to write down. We wouldn't get lunch. And so I'm going to just stay on the slides for this one. We want the force on this top left sodium ion. Its force on this top left sodium ion is going to be the sum of three forces due to the three interactions it has with the three other ions. So there's an ion below it, and there's an ion to the right of it, and there's an ion, a sodium ion, another sodium ion over here at the opposite corner to it. So each of these pairs creates a Coulomb law force. So there'll be a force due to this bottom charge, a force to this right charge, and a force due to this opposite charge. And it's those three forces that we want to add. So the first thing I did was picture those forces, and actually I quantified those forces. So this charge down here and this charge up here, the purple and the green, they're opposite charges, so there's going to be an attractive force on the sodium ion due to the charge below. I represented it by this green arrow here. You can see it's attractive. There's another attractive force due to on the sodium ion, due to the chlorine ion on the right. I've indicated it here. Again, it's an attractive force that's pointing towards the other charge. And then the third force is due to the sodium ion, the like charge that's at the opposite corner. That's going to be a repulsive force. And so I indicated that in magenta here because it's coming from the sodium ion. So that's the first thing. I drew the directions of the three forces. But I did more. I drew the size. I tried to reasonably accurately draw the sizes, and I actually annotated with the sizes, the relative sizes of the forces. So to help me in solving this problem, I defined a helper, a helping quantity. It's this lowercase f. Lowercase f is just the size of the force between two charges Q and Q, separated by a distance a, the spacing of our crystal lattice. So little f just is a shorthand, that's all I'm using it for. It's a shorthand for writing kq squared over a squared. I don't want to keep writing kq squared over a squared, so I'm just going to write this lowercase f. I picked that because that kq squared over a squared, that little f, is the size of the force due to this bottom left charge. It's at a distance a away. The two charges are both size q, and so this force is kq over a squared. This force that I called force number 2 due to this charge 2 here is little f. The same applies to this force number 1 due to the right-hand charge. This charge is a distance a away. The two charges' signs are q, and so this is also kq squared over a squared, or this little f. This force, due to the other sodium ion, this is actually smaller than kq squared over a squared. It's smaller not because the charges are smaller, not because the Coulomb constant is any different, obviously. It's just smaller because, look, this distance is the square root of 2 larger. This is just a bit of geometry. But this distance, this hypotenuse here, is the square root of 2 times a. If I square that up, that's 2a squared. That's in the denominator. And so that force is half the size, half of lowercase f, compared to the other two forces. Is all that okay? So that's just a handy shorthand that'll stop us writing out lots of stuff. Our job now given this, so I've constructed this picture on this slide basically with the sizes and the directions of the individual forces. Now we've just got to add together the three forces, 1, 2, and 3, due to the three charges, 1, 2, and 3, to get the resulting force. That's our job now. Okay. This slide, I write out the forces. We did this before with my device for measuring charge. I'm going to write out the forces in their horizontal and vertical components, x and y components. This is a way of managing, organizing the addition of forces. And you've met this in 211. You loved it in 211, I know. So we're going to use that resolution of forces into horizontal, vertical components, x and y components, to add these forces together. That's the only thing that's remaining in this problem. We know what all the forces are, we know the sizes, we know the directions. We've just got to add three vectors together. That's as simple as it. It's almost like adding 1, 2, and 3, but they're vectors, unfortunately. Okay. I got three lines here. This is where I resolve force number 1 to the right into x and y components. This is where the second line, where I resolve force number 2 into x and y components. Third line, where I resolve force number 3 into x and y components. So same principle in each of them. Look, for the first two, it's easy. Force number 1 just points towards the right. The whole force is in the positive x direction. So F1x is the lowercase f, F1y is 0. It doesn't point up or down. Similar idea for force number 2. It just points straight downwards. So the whole force is in the downwards direction. I call that the negative direction. F2y is minus f. There's no component in the horizontal direction. F2x is 0. So those are kind of easy. There's no calculation there. I just read it off the diagram. Little bit more complicated here with force number 3. It points up and towards the left, so it has a positive x vertical component, a negative x component, but I can just use the sine and cosine of 45 degrees to find the adjacent and opposite sides, which are the vertical and horizontal components of this triangle, and that will tell me the two components of F3. So F3x is here, F3y is here, F3x is just F3, its size, times cosine of 45 degrees, F3 times sine 45 degrees for the vertical component. Look, the minus signs, the plus signs in these equations here, I put all those in by hand by looking at whether the force pointed up or the force pointed down, getting very scared, or the force pointed left and the force pointing right, because I've got to finish this problem. Everybody okay with that? Just resolving forces into components. I can trivialize it like that. Okay. Once you've got forces in component form, they're really easy to add up. Adding up the x components of forces is adding up numbers. So that literally is 1 plus 2 plus 3. Adding up y components of forces is literally adding up numbers. That is easy, just like 1 plus 2. And that's all I did here. So this is a slide that just has the vector addition of the components. So the resulting force's x component is the sum of the three x components. The resulting force's y component is the sum of the three y components. I'm getting closer and closer to the door. I want to go over here. So all I got to do is add up the three x components to get FRX, the resulting force's x component. Add up the three y components to get the FRY, the resulting force's y components. And here I did that. They both come out to have a size of 0.65 lowercase x or minus 0.65 lowercase x. The signs mean, I pictured that vector, resulting vector here, it's towards the left and it's downwards. So it's a bit towards the left and it's a bit downwards. If we want the magnitude and direction, now that's just Pythagoras and trigonometric functions. If I want the magnitude, I can sum FR's x and y components, sum of the squares, and take the square root. It comes out to be 0.92f, which is this expression here in terms of charge and separations. And the angle comes out to be, if you take the inverse tangent of the x and y components of the vector, that comes out to be literally 45 degrees. It's pointing towards the center of the nanocrystal. We just discovered that that top left ion, sodium ion, is being attracted towards the center of the crystal. All the other ions, if we did the calculation,